Okay, let's just dive straight into this. Welcome, Gen Z Accounting Squad, to the explainer that's basically going to be your ultimate cheat code for the Management Advisory Services, or MAS, section of the LECPA. If you're a second or third year BS accountancy student right now, you already know the deal. The board exams are built to test not just what you know today, but how long you can actually retain it and how fast you can analyze it under intense pressure. So today, we're breaking down one of the most mathematically heavy subtopics you're going to face: cost estimation using regression and correlation analysis. My goal here is to help wire your brain to retain this exact knowledge for the next 3 years, straight into that exam room.
Here's our battle plan for today's explainer. We've got 1. The mixed cost dilemma. 2. Least-Squares mechanics. 3. Correlation, the R. 4. Goodness of fit, the R squared. 5. Predicting total costs. And 6. LCAPA rapid review hacks. Let's get into it.
Section 1. The mixed cost dilemma. The boss fight.
So, a mixed cost contains both fixed and variable elements, right? But here's the trap. As activity levels change in a business, the total cost behaves in a really messy way. You can't just guess what's going to happen. To actually strategize, management accountants need a clean formula. We literally have to mathematically separate those fixed and variable elements so we can predict future behavior accurately. Which brings us right to our ultimate weapon.
Section 2. Least-Squares Regression mechanics. The weapon.
The Least-Squares Regression method. Look, board examiners absolutely obsess over testing this exact phrasing, so let's break it down. It's a statistical technique that mathematically determines a line of best fit. But how? By minimizing the sum of the squared deviations between the line and the actual data points. Seriously, burn that exact phrase into your brain right now. Minimizing the sum of squared deviations. That is your golden ticket to identifying this method on a tricky multiple choice question. Okay, so here is the classic cost function you'll be using. Y equals A plus BX. Let's map this out spatially in your head so it actually sticks. Y is your total cost. It's the dependent variable because, well, it depends on whatever else is happening in the business. X is your activity, or cost driver. That's the independent variable. Now, A represents your total fixed costs, which is visually your y-axis intercept on a graph. And B is your variable cost per unit. Visually, that's the slope of the line. The steeper the slope, the higher that variable cost per unit is. Make sense, right?
Now for the heavy lifting. The least-squares method actually uses a system of 2 equations to find those A and B values. Equation 1 is the sum of y equals n times A plus b times the sum of x. And equation 2 is the sum of xy equals A times the sum of x plus b times the sum of x squared. If they throw a computation-heavy problem at you on the LECPA, you are going to need to pull these equations purely from memory. Honestly, write them down, stick them on your bathroom mirror, and just memorize them. Because once we build this mathematical line of best fit using these equations, we have to figure out if that line is actually useful.
Section 3. Correlation analysis. The R. Decoding the metrics.
Meet the coefficient of correlation. We just denote this with a lowercase letter r. Think of R as your scout. It goes out and tells us the relative strength and direction of the linear relationship between our 2 variables, so our cost driver and our total cost. It's basically asking, hey, are these 2 things actually moving in sync or not?
And the value of R is always going to fall within this specific range, negative 1.0 to positive 1.0. A positive 1.0 means you've got a perfect, direct relationship. Picture an upward sloping line going to the right. A 0, that means total randomness, just noise, no pattern at all. And a negative 1.0 means a perfect inverse relationship, so a downward sloping line.
But listen closely to this part, because this is a massive trap examiners will absolutely set for you. Correlation does not equal causation. Just because 2 variables correlate perfectly on a math level, it absolutely does not prove that one caused the other to happen. It merely indicates a linear relationship exists. That's it. Do not fall for those trick answers that try to claim R proves cause and effect.
Section 4. Goodness of fit, the R squared, the ultimate confidence check.
So while R gives us the direction, we still need a confidence check. Enter the coefficient of determination, also known as R squared. Let's unpack this definition slowly together. It is a measure of goodness of fit. Honestly, if you only remember one single concept from this explainer today, make it this. R squared indicates the percentage of total variation in the dependent variable, your costs, that is explained by the regression equation.
And because it's a squared number, its range is strictly positive.
It goes from 0 to 1.0, or 0% to 100%. The closer r² is to 1.0, the better. It means we have way more confidence that our independent variable actually predicts the behavior of our dependent variable.
Comparing these two side by side is an absolute must because board examiners love to mix them up in the multiple choice options. On the left, R is all about direction and strength, ranging from -1 to +1. On the right, r² is all about goodness of fit and the percentage explained, ranging strictly from 0 to +1. Keep these two perfectly distinct in your head.
Okay, let's do a quick active recall check. Say you run a regression analysis and your r² comes out to 88.36%. What does that actually tell us about our cost driver? Just take a second and answer it in your head. Got it? It tells us that exactly 88.36% of the variability in our total cost is explained by that specific cost driver, meaning it's a highly correlated, super reliable model.
Section 5. Predicting total costs. The victory.
We've got the formula, we trust the metrics, so let's actually predict the future. The crucial part here is just plugging it all in. If our regression output tells us the intercept is 236,837 pesos and the slope is 3.7625, we just drop in our expected activity level. Let's say 20,000 machine hours. You multiply 3.7625 by 20,000, add the fixed intercept, and boom, you've successfully predicted your cost. Oh, and here's a massive LECBA computation hack for you. If a problem throws standard error at you alongside these line functions, just ignore it. Standard error is completely ignored when calculating the estimated cost using the y equals a plus bx formula. Don't let it trip you up.
Section 6. LECPA Rapid Review Hacks. Final Boss Preparation.
Treat these next points like mental flashcards for guaranteed easy points on the exam. First up, Least-Squares Regression gives the most mathematically precise cost estimate compared to, say, high-low or visual fit methods. Second, if you see a data point falling far, far away from all the others on a scatter diagram, that's called an outlier. Third, multiple regression analysis involves one dependent variable and many independent variables. And fourth, simple regression analysis involves one dependent variable and just one independent variable. Lock those definitions in right now.
As we wrap up this explainer, I want to leave you with this final thought. How does accurately predicting a seemingly random mixed cost change the way a business ultimately survives? Because remember, mastering these formulas isn't just about passing the LECPA, though you definitely will do that. It's about becoming the strategic partner who can look at total financial chaos, find the mathematical line of best fit, and literally save a company from going under. Keep grinding, keep reviewing those formulas, and I'll see you in the next explainer.